very pleased to welcome Benjamin, who's already been an important part of this conference since Friday, I think. Yeah, he's been taking part in a lot of things, but I think this is going to be your most technical contribution so far.
A bit.
By a bit, yeah. And I think it's best if I let you introduce yourself and say where you're from to the audience, so please welcome Benjamin.
Hello everyone, I'm Benjamin. I come from the far-off land of South Africa, so I've never been down that way. My background is, I've been Python heavy developer since 2015, so about a decade. I've worked, bulk of my career was actually spent at Uber, and then Aurora, which is another robotics company. But yeah, so today I'm going to talk to you about asyncio, and you're probably writing it wrong. And I bring this talk, and the reason this talk is very important to me is because I maintain a few open source libraries that are asyncio, and the community contributions that we get are really bad usually. And I think that the fundamental problem is that people do not think in asyncio. So you think in your standard synchronous imperative way of, do A and then B and then C and then D and so on. But asyncio is a bit different. It is inherently asynchronous. So I'm hoping to introduce you to a handful of the features of the asyncio library that maybe you're not using. So the title of my talk is Asyncio isn't just typing await. It's also typing async def. So thank you for coming to my talk. Just a bit about me. So a bit about me in terms of why asyncio is important to me. So 2018, I was at Uber. I had moved recently into the hardware team, where I was the primary software tools dev for hardware. And at the time, our AWS bill was something like US $2 million a month. And so in order to curb that, they limited hardware to a $5 a month AWS VPS. And so I had to do all of our tools using this $5 VPS, and it wasn't working very well. And so over Christmas break 2018, I was reading about asyncio, which at this point was still very recent in the Python ecosystem. I think async def and await keywords had just come into play. So anyway, so I switched our Flask server to Quart, which is an asyncio rewrite. I saw basically no speed improvement at all. And then I learned about the keyword, or about the function rather, asyncio.gather, which executes two things at once. So massive speed improvements. And that's where a lot of you maybe have stopped. That's where a lot of developers stop when it comes to asyncio. They get to gather, they say, okay, it goes faster now, goal achieved, no more reason to ever read about asyncio again. But there's a whole new world that awaits when you get a bit further in the documentation. So firstly, is asyncio right for my project? This is a big consideration you need to make before you start down this, because there's a very good chance it's not. So firstly, what asyncio is. So asyncio is just in Python, asyncio is just a library of high and low level functions that facilitate asynchronous input-output. Does everyone here know what asynchronous input-output means? This is good. That's great. The things that asyncio is not. It's not a magical tool to speed up your program, as I've learned by switching to Quart with doing nothing else. It's not a substitute for optimizing your code. In a lot of cases, actually, async I/O can be slower than synchronous code. If you're not doing input-output, doing everything in async I/O adds a substantial amount of overhead that you do not need, you're going to see no benefit from, and your code's going to run slower. So if you're not doing I/O, well, good for you, but it's not probably right for you. It's also not a drop-in replacement for threading or multiprocessing. We'll get to a bit more to that. So if you need to do threading, you need to do multiprocessing. Async I/O is not just a drop-in replacement to fix those. Here's some key reasons you should not use async I/O. Like I mentioned before, your project is not I/O bound. You rely heavily on libraries that do not support async I/O or have no async I/O compatible alternatives. This is very commonplace still. It's getting better. The ecosystem in the last 4-5 years for async I/O has dramatically increased. There's so many more standard libraries, not standard lib, but there's so many more like big time libraries that now have async I/O. So that's great, but there's still a lot that do not. Maybe you don't have the resources to rewrite your entire application to async I/O. It's kind of the turtles all the way down kind of problem, right? Where if you start to do async I/O, you kind of have to do the whole thing async I/O. It doesn't work great if you just try to make certain parts of it async I/O, and then the controller is still not running in the event loop. Yeah, so keep that in mind. You shouldn't go async I/O if you think it's going to speed it up. If you think it's going to just speed up your solution, but you haven't actually benchmarked or profiled your code. So you can use cProfile. cProfile is absolutely wonderful. If you have PyCon, it's built in, gives you a nice little graphic and everything that you can then ignore and then just read the raw data yourself. But it does give you that nice little graphic. You should, if you're doing benchmarking, which you should design your benchmarks that match real-world scenarios. I know we've all looked at different libraries that compare JSON encoding speed, mu.json versus or.json versus standard lib, and you're like, oh, well, I must use or.json. That's the fastest one. I see it right there. These benchmarks are not necessarily applicable to your given use case. So you should create your benchmarks based on how your use case is going to go. A benchmark with no real-world application is meaningless. It's just a number on the screen. Go play with a calculator. So now let's get into the code. So if you do have a computer, you're welcome to pull it up. I did. So I just added like a DNS forwarding for pycon.bdheims.com. Hopefully it's active. If it's not, the github.com/thewhalekings/pycon async IO talk. And then let me pull it up here. Okay, so this is a Jupyter notebook. I'm assuming everyone here is familiar with. Oh, I don't know how to increase it.
Command plus.
No, not working.
You need a hand for somebody to hold the microphone while you type?
I just want to see if I can. Sorry.
So command plus isn't in the tree.
Is it big enough? So yeah, so this is just Jupyter Notebook. Anybody unfamiliar with Jupyter Notebooks? Cool, great. Yeah, so this is just kind of does our setups, here, and you know, it's just a function that we have to kind of time various things. And so this is where we really start, right? So this is your typical way that you're doing things synchronously. You're just, you know, pulling, you know, sync.get. This server, I mean, you can obviously look at the code, but it waits a given amount of time and then just sends back the response. Right, so yeah, so we've got that. So this here is probably you know, how you would start refactoring this, right? So you're starting here. You've got your, maybe you've got requests. You've probably got requests. You're doing requests.get and you're pulling data, and you say, okay, well, I want to switch. I want to switch to async IO. Done my benchmarking, I promise. Done my profiling. You know, it's all great. I need to switch to async IO to see significant speed ups. So you'll add this, right? So you'll switch to AIO HTTP or HTTPX or something like that. And you can see, let's just see here. So you can see this has taken 0.5 seconds. And it takes 0.5 seconds because this server.get takes 0.5 seconds. And then returns some random integer around 1 million. So you might say, well, I actually need to not just get from one source, I need to get multiple. And so you just stop popping in that await keyword everywhere. Let's take a look here. And you can see this is taking 1 second. Obviously, 0.5 plus 0.5 is 1. Yeah. So this is the first async IO optimization that you're likely to encounter. It's certainly the one I did. Right? It's async IO.gather. Does everyone here know? If you feel free to raise your hand when I say this. Does anyone here not know what async IO.gather does? Okay, that's great. So async IO.gather adds 2 coroutines. Well, adds as many coroutines as you specify. Does everyone know what a coroutine is? Okay, so coroutine, or so this is a coroutine function. So this async def, then the function name, defines a coroutine function. So when we call it, it doesn't actually do anything. It just says, I know what I'm supposed to do, but I'm going to wait for you to actually add me to the event loop and then, you know, see my result. And that's what await does here, right? So when we're awaiting sequential, we're actually doing 2 things in this single line. So we're creating the coroutine by calling the coroutine function sequential, and then we're awaiting it. So we're immediately adding it to the event loop and then getting back the result of it. So this is kind of, it's just a quick way of basically creating this coroutine and then getting the result. What async IO.gather does is everything that you put in async IO.gather. So it's, you know, it takes as many args as you specify. It puts all of those, it adds all of those immediately to the event loop, and then will only return after they've all completed. But they're all running concurrently. So there's no, so what do you guys think will happen? Again, here, we're doing server.get twice. So, and we did server.get twice here. We've seen this takes 1 second. And it takes 0.5 seconds to execute one of these coroutines. How long do you think this is going to take? Again, this is the same result as up here, but we're piping this through async IO.gather. So Who can take a guess as to how long this is going to take?
Half the time, but I think it's also there.
Pretend you didn't see that. But yes, half a second. Why does it take half a second? Can anyone tell me why? Exactly, exactly. So we are running these at the same time. So there's not actually any CPU processing or anything going on. We're just waiting for the server to return our data. Well, this is a simulated server, but you know, it's still the same. And so when we run this, we can say it has taken 0.5 seconds. And that's because, again, we're executing them at the same time, getting back the results when all of the things in there have completed.
I have a question. Sorry.
Yes?
What really happens behind the scenes? Like, I don't know if you can go a bit deeper on this tech here.
I can. Okay, so there's a thing in Python called the event loop. And the event loop keeps, it's basically a while true loop, right? And so while true, execute everything or check for the results of everything that's in this event loop, right? And so when we add these items to the event loop, such as with asyncio.gather or even just with await, what that does is it adds it to this, we'll call it a list, right? It adds it to this list, which Python then goes for item in list, check if done, return. So when we add these items to the event loop, and then depending on when we're calling await, actually depends on when our program gets them back. So we've made the request, and then we've moved on to the next one. We've not actually checked the results of the first one yet. We've made the request, and then we are moving on to the second one to make that request. Because we've only got 2 requests in the event loop, we just pop back and forth between the two to see, have you returned the data yet? No. Have you returned the data yet? No. Have you returned the data yet? Oh, you have. Have you returned the data yet? Oh, you have. Great. And then both of those coroutines return. So that is a very high level, very quick way of explaining the event loop. The default implementation is the asyncio event loop, which, so if you just call asyncio.run, that uses the default event loop. If you're doing a ton of things at once, there's a library called UV loop that is written in Python that works really, really nice. It's significantly faster, but again, only if you're benchmark, profile. If you don't get any benefits over it, why include the requirement? So that is what gather does. So this, I don't know if you saw when I was here. So I've got two items here. So this basically just simulates doing some CPU intensive application in Python. We don't really care for the result. So basically just loops over n number of times, gets the sine, cosine, and square root, adds those two. So it's not very efficient. So if you're like, oh, well, it doesn't matter, right? It's just an example of CPU intensive code. And then this is basically the exact same thing, but in GIL-less Python, right? And so you can see here, we have this no GIL, and this will come into play just now. So again, maybe we want to do some data processing with asyncio. So we're going to pull the data in. We're going to crunch it with the pure that I showed, and then we're going to get the next set and then crunch that. You can see it's taken 1.27 seconds. Now, this is not a talk on Python for the record. This is the example really has nothing to do with that. But this is significantly faster with Python. 1.03 seconds. So that's only 0.3 seconds of processing time. So remember, this takes 1 second. So much, substantially faster. That's really not the point though. The reason that this is super important is because we're going to optimize, right? We're going to do all our async. We're going to pull this directly, and then we're going to crunch. 0.77 seconds. Not terrible. You know, much faster than 1.23. And if we do the same thing, exactly the same thing with Python, we can see, oh, 0.52 seconds, so much faster. The big difference here is that because, again, do you remember that we declared no GIL in the Python? That allows us to do this wonderful thing called asyncio.toThread. Now you can do this with things that use the GIL as well, but you're not going to see the same benefit. Because we're releasing the GIL in that specific instance, what we're able to do is we're able to use system threads to do as many concurrent, you know, basically as many concurrent cores as you have, or hypercores in terms of Intel or whatever, but more or less, you know, as many. So it's a super simple way, or a much more efficient way of doing multiprocessing. If you guys have ever done Python multiprocessing, it's not fun. It's not that good. Nobody enjoys it. So this is a much more efficient way of utilizing these extensions that we might write to do that CPU-intensive coding in our asyncio program. And there's just no real way to do this outside of asyncio. And so we see here 0.52 seconds. Yeah, so again, because it goes so quick, we're going through it very, you know, we're not going to see the same benefits that we might see in the real world, where we can say, you know, hand off thousands of tasks to threads, but it's going very quick. This is, you know what, I'm actually going to skip over this because for the sake of time, because you're not really going to use this. So let's say, I actually had a conversation with another attendee earlier on using asyncio. It's made their application too efficient. They've optimized too much client side, and now it's causing issues. The backend just can't keep up. Well, there's a way that we can restrict. There's a couple ways we can restrict, right? We can just write it synchronously, or you know, in the case up here, we can use a different loop executor, but it's much more efficient and much simpler, generally a more Pythonic way to create a semaphore. So, does everyone know what a semaphore is? Threading or asyncio? Okay, so it's basically, it's just an object that says, I have a certain number of me, and only that number of me can be active at the same time. So we can use this to declare, so here we created an async semaphore with 20. So now, when we created a coroutine function that takes this, we can async with sem and then actually execute. So what this async with sem here is doing is basically saying, hey, when you're available, you know, if I'm within this 20 limit, you know, allow me to actually utilize the resource here, right? So it's a really, really helpful way of getting around any kind of restrictions you might have. Maybe that's you know, that you can only have a certain number of requests per second, stuff like that, right? And so we can see if we execute this. So actually, wait here. So without the semaphore, it takes 0.5 seconds. That's very quick to do 100 tasks, right? Now with the semaphore, because again, we're limiting it to 20, see it takes much longer. But again, because we're only able to do 20 at a time. The next slide, again, if anyone has questions along the way, feel free to interrupt me. So a thing that I find super, super useful to use in asyncio based applications is asyncio queues. Has anyone used a queue before? It doesn't have to be asyncio, it doesn't have to be Python. Has anyone used a queue before? Great, great. You guys understand queues then. Right, so typical in the design structure is a consumer queue, a producer queue, right? So we're dumping our results, as we're going along, we're putting the next item in the consumer queue, it goes and fetches the data, puts it in the producer queue to actually process the data, and then returns it all. And so it's a bit complicated, but it allows us to kind of continuously iterate. I work for blockchain a lot, and so if I need to pull 6 million blocks worth of data, I dump them into a queue because it's just much simpler to keep in control. Right? And so we'll keep it with like a number of threads or a number of workers, and we can see I'm getting close on time. So it takes quite a while to actually run this example. And it's much more complicated. But you can look at the code in on your own. But you can see we complete a lot of tasks in not a whole lot of time. It's 13 seconds, but the reason for that is it does make more sense. Sorry, quickly trying to get through. So using tasks instead of just raw coroutines. So remember I said, before, the coroutine doesn't actually do anything until we've called await. That's not universally true. What we can do is we can create a task, and then we can create a task of the coroutine as we define here, right? And so what this does, this query tasks, it makes 100 tasks, asyncio tasks of the coroutines. Now what do tasks do? They add them directly to the coroutine and then immediately start executing them. They add them immediately to the event loop, and then as they're added to the event loop, as it gets to that next task, it starts executing them. So you notice we're not actually calling await here at all, right? But every single one of these has started. If we hadn't done this loop.create task, those wouldn't have started until we get to this next line. Right, so what it's doing here is it's just gathering those tasks. So just trying to wait for the results of the tasks. And then we go through here and it crunches them, does the data processing. And that's a good way of doing things. It's a very good way of doing things, especially, go ahead.
What do you mean by good? Like, is it faster?
Well, it can be, right? I guess I should clarify that, right? So imagine you have two data sources. You need to process two of them. So you need to collect 3 items of data. One from one data source, 2 from another. You actually need to do a lot of processing on the two items that you're getting from somewhere else. Well, it might make much more sense to create a task at the beginning of your function to go fetch that other lighter data source. Just create the task, don't do anything with it yet, and then await like asyncio.gather those other 2 from the other data source. So those come back. So those come back to you. That's great. My computer's gone to sleep. Sorry. So those come back to you, and meanwhile you stop processing that, and then you are checking for the results of the task. And you just needed to pull from another source, right? Because otherwise, you had then, if you're piping all 3 of those into the same asyncio.gather, what's happening is you actually have to wait for all 3 of them to complete before you can start processing those 2 that are kind of important. Does that make sense? Yeah. So a way of just adding it, saying, hey, we need it, we're going to need this data later, so start running it, but we don't need it right now. Okay, that is all my time. I don't have, there's a couple more examples, but sorry, I'm out of time. Thank you guys.
Thank you very much.